So I'm flipping back over to that. Normally I'd ask you a lot of little questions and we'd get through this kind of slowly, but I want to go through this quickly so you can talk about your cars more and plan them. Okay, Newton's first law, you've heard most of this before. Objects in motion remain in motion, blank, and objects at rest stay at rest unless blank. So this is just laying out what happens to an object if it's moving or it's at rest. And this whole first part until here is if nobody's bothering the thing. This last part is if somebody's bothering the object. So for the first part, if I take a bowling ball and I throw it out in space, nobody's going to bother it in space. It starts moving. Is it going to get faster, slower, or stay the same?
Stay the same.
Stay the same. So that's the first part. It's going to remain in motion at a constant speed. And not only is it going to go at a constant speed, but is it going to curve or what?
Nope.
It's going to go and in a straight line. So this first part is just all about what happens if nobody bothers stuff. But that's what happens to a moving object if nobody bothers it. And if an object is just sitting there and nobody bothers it, it's going to keep sitting there. So now, if somebody bothers it, then they'll do other things. They'll turn, they'll slow down, they'll speed up, they'll start moving, that kind of thing. So this is what happens unless it's acted upon by an unbalanced force. There are other ways to say this. Sometimes people say acted upon by an outside force. And I like to say acted on by a net force, because we're going to be using the term net force a lot. It's unbalanced, it's kind of like net. And to just really quickly talk about balanced forces right now. Forces, there are two forces acting. They're balanced. Tell me when they're suddenly unbalanced. Yeah. Suddenly the force of this hand pushing that way was stronger than this hand pushing this way. But when they're pushing the same, they're balanced, nothing happens. They're at rest, they stay at rest, unless there's some imbalance that starts to happen. These two things are just laying out, they're really restating that, but I think it's important to go through this, laying out what something can be doing if the forces are balanced. So if you have balanced forces, there are just two options for what you could be doing. Like this camera sitting here right now, the forces on it are balanced, so it's sitting still. That's one thing something can be doing if the forces are balanced. And there's only one other option. If you're not sitting still and the forces on you are balanced, what do you have to be doing? What's that? Keep moving how? Constant speed in a straight line. So those are the two options. Moving at constant speed in a straight line. And a better way, without listing two things, a better way to really sum this up is that there's no acceleration going on. Acceleration is really the key to everything. If something is accelerating, meaning it's speeding up, it's slowing down, it's turning, the forces are not balanced. You've got to have some outside, unbalanced net force to make you do that kind of stuff. Okay, so that's just something is if the forces are balanced. Now, if the forces on an object are not balanced, there are three things it could be doing. It could be turning. It could be speeding up. And the last one? Slowing down. It can be doing 2 out of 3, but it can't be doing all 3. And a quick and easy way to sum up all 3 of those is if something is accelerating, then the forces are not balanced. This whole page is just to make sure you understand the terminology so you can solve the problems and do stuff related to it. Newton's law of inertia, that's the other name for Newton's first law up at the top of the page. And inertia is, talked about it a little bit with the C-clamp, it's resistance.
How did he figure this out?
Me?
No, how did Newton figure out that?
Let me write it down, and then we'll talk about that. Resistance to change in motion.
Was Johannes Kepler Newton's student or whatever?
I don't know. I should know that. We could look it up.
I feel like I don't know. If
All those.
How do you figure
they
out?
work
who's
together
more
and
strong?
study the planets and their movement. I'm pretty sure, and like
There's a part in the book that talks about this. I think it's Galileo who really was he was the one that laid the groundwork for this.
How do you know
And
that?
he did things with balls on ramps, and he had them going down one and coming up another one, and then he thought about, well, what would happen if I just let it go down and then go on the flat ground? Would it go forever? And so it was just observation, and eventually, that it wasn't just Newton. Newton built on the works of those other guys.
it was a lot of studying space.
Yeah,
too, and
thousands of years to figure
planets
this
and
out.
stuff, and revolve around the
And
sun.
it's going to seem kind of obvious to us, and those guys are going to seem kind of dumb in a way.
No,
It doesn't?
seem obvious, 'cause, like,
So something moving, it's going to keep on moving
yeah,
unless
that's-
something
I
stops
can understand
it.
something that stops, stays, stops, doesn't move.
I mean,
right? How do you
they had
figure
these
out if it goes
ideas
on
that-
forever? Like, it doesn't-
Yeah, they
Right.
don't
How do
have
you-
the ability to have that.
You don't
Right.
have it exactly.
Yeah.
I guess they
So
didn't
how do you
really,
figure that out?
They weren't
Right.
really like, into all like the gravity.
Well, good. I'm glad you have a respect for them. I always thought, yeah, that's obvious. But we grew up in a different time. I'd have to research that more to tell you exactly how they figured all this out. So resistance to change in motion. Inertia can be any kind of inertia. We're just talking about physics inertia. But inertia is if you try to get somebody to do something, like I try to get my son to put his bike away. And he just really wants to keep sitting there, and it's hard to get him going. But once he's going, he keeps moving. He has a lot of inertia. He has resistance to change. And once he's playing something that he likes, he's making his fort in the woods, I can't get him to stop and come back in. So he has inertia. I have it with sleeping. I have a hard time getting to sleep. But once I'm asleep, I just don't want to wake up. So what kind of things have the most inertia? I'll give one example. A dump truck. You can, whatever you write here just doesn't really matter. What's something else that would have a lot of inertia? A blue whale. Very good. Blue whale. Try to stop a blue whale. The Earth. So these things all have, what they have in common is that they are massive things.
The sun moves a little bit.
The more mass you have, the more inertia you have. And the harder it is to start it moving, and the harder it is to stop it from moving. Which, I was having this discussion with somebody about cars last class. Is it a good idea to have a heavy car or a light car?
Power to weight ratio, it doesn't matter. If you got the power, it
If
doesn't
you,
matter.
the good thing about a heavy car is if you get it moving, it's not going to stop. The bad thing about a heavy car is
If you get it moving,
it's hard to get it moving. So,
Or the bad thing is you get it moving.
force vector. What is a force vector in this class? It is an arrow representing a force in some direction. So,
It's like the two arrows pushing on the
yes, or if when I had my hands pushing against one another, we could have had an arrow showing which way my left hand was pushing and an arrow showing which way my right hand was pushing, and whatever numbers we put by them would have to be equal because they were balanced. And then the net force, this is really an important concept. The definition is going to be kind of screwy, and you may not know what I'm talking about. It's the sum of the force vectors. Ooh, I'm going to put vector sum. You're going to hate. I'm sorry for this. Vector sum of the forces acting on an object. I'm sorry.
What?
So, just to give you an example of what I mean by that is if, like with my hands earlier, I had a force of, I'm just going to guess, 20 newtons going that way, and I had a force of 20 newtons going this way. Now the sum, just the mathematical sum, is 40, right? Guess what the vector sum is? 0, because this is 20 to the right and that's 20 to the left, and they cancel each other out. Or in other words, this is like a plus 20 and that's like a negative 20, and you put them together and you get 0. That's what vector sum means. A basic unit of force, you should know this from 9th grade, Newton. And the abbreviation you should know, but hardly anybody knows this. I don't think I've asked anybody who's known what is a Newton. If you were to pick up a Newton, how heavy would it feel? You're going to be able to use 22 newtons of, 100 newtons of force in your cars. A newton is about a quarter of a pound. It's a little less. It's really 0.224 pounds. But we'll just imagine it's about a quarter. And if you have trouble visualizing a quarter of a pound, it's like the weight of a raw hamburger patty before you cook it. If you take the patty out of a quarter pounder, it's going to be less than that because they dry out, unless it's soaked in special sauce or something. Okay, so that's kind of irritating stuff. This next part, this is to see if you get it.
You draw these?
What's that?
You draw these?
They're beautiful, aren't they?
They're actually pretty good.
I even put them out of order. I listed C first. So this is just to drive home the ideas of vector sums and balanced forces and unbalanced forces, things like that. So A says to look at the pictures, decide whether the forces are balanced or unbalanced, and label them. And then B says if there is an unbalance, then there's going to be a net force, and draw an arrow representing the net force. So looking at A, which is not the first one, but it's the first letter. What do you think? 600 newtons pulling to the right, 400 to the left, balanced or unbalanced?
Unbalanced.
Definitely unbalanced, so put a big U there. And now I want to draw a vector and label it to represent the net force.
Did you say like 200 newtons?
200 newtons which way?
To the right?
To the right. And if you don't understand why that is, I'm going to try to explain it in a different way. This is a stronger force, this is a weaker force. So the vector shows us which one is winning. If this one's 600, that one's 400, this one's going to win, and the rope is actually going to move this way. So overall, those two forces put together, this one gets totally canceled out. There's a little bit of this one left, and what you have is the rope's pulled that way with 200 newtons. Think of this as kind of like the scoreboard, a weird scoreboard where you've got two teams. This one's got 600 points, that one's got 400 points. This tells you who won and by how much. So this is the winner. They won by 200. Let's do B also. So B, you've got a ball that's falling from the sky. The weight is 50 newtons, pulling it down. The air's got 50 newtons of air resistance pushing up. Balanced or unbalanced? Balanced. Those are the same and opposite, so those are balanced forces.
So would that ball just be floating in the air then?
So what is the ball doing? That's a really good question. I was going to ask you that. According to Newton,
moving at a constant speed. Right?
yeah, according to Newton's first law, if the forces are balanced, it could be doing two things. It could be sitting still, or it could be moving at a constant speed in a straight line. So what this ball's doing is it's reached its terminal velocity. It's moving at a constant speed downward in a straight line. Now, if it were not moving to begin with, it would continue to not move. But we can tell that it was falling, so it's just going to keep falling. It's not getting faster or slower, though. But it doesn't just stop. So you do the rest. Do D, E, F, and G.
What do I see?
And C, yeah. And then we'll talk about those and do the last part.
Would you ever say like
Is that 60?
negative newtons for it going in
Yeah.
a certain direction? Or
Uh,
just always, like,
No, you
negative
just
newtons in your
you
head?
would well you could instead of having this drawing, you could say the force of gravity is negative 20 newtons, and the force of drag is 15 newtons. Yeah. If you're writing out problems and you can't just draw it in your math that you're doing, you call up positive and down negative. For now, you don't have to worry. And once more, this is not on this next test. It will be on a test in the future. The ball?
Yeah.
The roller picture.
I know some of you are still working, but I want to kind of rush along to let you work on the cars. What about C? Balanced or unbalanced? Unbalanced. And the downhill force is stronger, so it's the winner. This one is stronger than that one, and the difference is 50. So you get a 50 Newton downhill force, and that's unbalanced. So D, this one, the ball's in the hand. The weight of the ball is 1 Newton down. The hand force is 3 Newtons upward. So balanced or unbalanced? Unbalanced. And the net force is which way? Up. And what is the net force? 2 Newtons. E, got the car moving to the left. It's moving to the left, but that doesn't mean the net force is to the left. In this case, friction is slowing the car down. It's pushing back to the right. With 300, engine's pushing it to the left. The net force is in the direction of the stronger force. It's going to be 100 Newtons. And these are unbalanced forces because they're unequal. G, friction pushing up with 40, gravity pulling it down with 40, the forces are balanced. So the net force would be 0 there.
Why'd you change, in B to F, why'd you change it from air resistance to drag?
I don't know. 2 different names for the same thing. Drag is the name for friction from some fluid that you're traveling through. So you can have drag in water, you could have drag in the air. Okay. This is just a specific name. Good question. You could call that air resistance. You could call that drag. So force is balanced or unbalanced in F? Unbalanced. Which way is the net force? Down, and it's 5 Newtons. Now for what let's do this one, and then we'll get to what I think is the trickiest part. Forces are balanced whenever the net force on an object is 0. So 0 net force means the forces are balanced. Okay, this is what I think is the hardest part. You have to tell what's happening to the motion. 3 says the ball in picture C is rolling down a hill. What does the net force tell you about the ball's motion? So look at it. Here's the ball rolling down the hill. The net force is downhill. What I'm getting at is the ball going to accelerate, decelerate, or move at a constant speed? So it's being pushed in the same way it's moving, so it's going to go faster. This ball is going to accelerate. So it's accelerating. And see if you can do, actually let's do 4, and then you do the rest. Ball in picture B, this ball is falling from the sky. The forces are balanced. There's no net force. Is it going to accelerate, decelerate, or keep a constant speed? Is this ball going to speed up or slow down or stay the same? Stay the same. If there's no force, no net force pushing it down, no net force pushing it up, it's going to stay the same speed. So it's going to keep falling as fast as it's going now. Constant velocity. So do 5, 6, 7, and 8. And then after that, get your car drawings out.
Did you hear about they're making a train? You're supposed to be able to go over. It's going to be in a vacuum sealed tunnel, so it's going to have 0 air resistance. 0 air resistance. No. So it doesn't.
When you get the car stuff out, don't put this page away. I want you to check your
pushing any air around the room. You don't like vacuum with like no air at all. That's what's going to be traveling. And it doesn't even touch the rails. It runs on that. So you have like minimal.
To simplify this, if the net force is the way it's going, it's going to speed up. If the net force is the opposite of the way it's going, it's going to slow down. If the forces are balanced, it's not going to do anything. It's just going to keep doing its good. Not going to change. And if you're lazy and you want to write A, D, or CV, you can do that. I have to write the whole word. Trickiest one,
Okay,
I think,
what
is
if
number 5.
What if you have a force and it's pushing
How do you get it so that it stays constant speed? Is it
Balanced forces. So if this was 3 and that was 3, the ball wouldn't go anywhere. It would just keep sitting there.
Does that mean that something's always accelerating? Like, can you have something be at a constant speed?
If, in this case, since these are the same, it's going to go at a constant speed because it's moving. But if it weren't moving,
Which way is it moving?
it's moving down. It's falling. It says ball is falling from the sky. What does the force tell you?
But if I thought if the same amount of force pushing it up is down, then it doesn't move.
If it's moving, it'll keep moving. If it's still, it won't start moving.
Oh, so this is okay. So this is the inertia something that it keeps doing. Understood. So like, if you throw a ball and it goes, and there's no friction. No, I get it. You call it.
Left all in.
Time to check your answers. I know a couple of you haven't finished all of them. I'm going to actually add something on the other side. Up here, when forces are balanced, you don't have to add this, but I think it just makes it maybe a little bit simpler. Another way to say this is no change in motion. And when forces, can you be quiet? When forces are not balanced, then motion changes. Motion changes is another way of saying there's acceleration going on. No change in motion is another way of saying there's no acceleration going on. So with all these, if I have a B written next to it, it's going to keep doing what it's doing, whatever it is. If I have a U written next to it, it's going to either accelerate or decelerate or turn, but none of these are going to turn. So the ball in the hand, we've got unbalanced forces here, so the motion of this ball is going to change. Number 5 says they have not been moving, so they're going to start moving. And they're going to start moving upward because that's the net force. So they're going to accelerate upward. Number 6, this is about E, the car is driving to the left. If you look at this car that's driving to the left, the forces are unbalanced, so something about its motion is going to change. If it's going to the left and it's got a net force pushing it to the right, is it going to speed up or slow down? Slow down, so it's decelerating. In G, we've got the box sliding down the hill. The forces are balanced, so that means there's no change in its motion, which means it's going to keep doing what it's doing, so it's just going to keep sliding down the hill. It's going to have a constant velocity. Sometimes I've said velocity here, sometimes I've said speed. People just use them interchangeably most of the time. Number 8, the ball's falling from the sky. This one, we've got unbalanced forces here. That means the motion is going to change. It's already falling. The motion, the net force is in the same direction it's falling, so it's going to accelerate. That force is going to actually speed it up, so it's going to accelerate. You can, right now you can sit wherever you want to with